This video is to help you understand better homework 28. There's a lot in our written homework advice that it's enough for you to do the problems, crank them out. But let's try to understand these problems better. And I really do need to remind you of dot products. A dot product primer. If I have two vectors, A and B, put their tails together, and then we can define an angle theta between them. The dot product of A with B is just the magnitude of A times the magnitude of B times the cosine of the angle between them. You could take this outside angle too, it would give you the same cosine. Therefore, A dot A is just A squared. It's like a vector with itself. Vector has the same direction, so the angle between itself is 0. And A dot B is B dot A. Didn't matter which direction we took them in. And here the distributive relation holds. A dot C plus D is equal to A dot C plus A dot D. I had a little fun just looking at the dot products on both sides in terms of these angles, and it wasn't too hard to show. It came from the definition of AB cosine theta. For our particular problem, we've got an initial mass m hitting an identical mass m, and the m's just cancel all out, so I can just talk about the velocities. V comes in, u and w go out for the this guy's final speed velocity, and this guy's final recoiling velocity. And I'm going to define the angle between u and v as psi. In our little proof, we'll end up with the dot product of u and w involving the cosine of psi. And if you can show that the cosine of psi is 0, then psi is pi over 2, but psi was just theta plus phi. In the second problem, you can see the written advice. You're just going to crunch through in parallel with the notes on page 3. By the way, you can just check that when you're done with theta plus phi, should it be greater than 90 degrees or equal to 90 degrees or less than 90 degrees? That will be a small check. In problem 3, what we're doing, we've got this thing balanced, this rod balanced, on vertically, and then we nudge it a little bit, and then it falls down and goes through, and whether it's just before it hits the floor or whatever, it has an omega, it has gained angular velocity. And the shortcut, the quick way to get it, since we don't need to know the time and we don't need to solve, the detailed trajectory in between as a function of time, we can use energy conservation as a shortcut. Because everything here there was no energy loss to friction. And the delta K plus delta U equals 0 when I've got mechanical energy conserved. And delta K, in this case, it's purely a rotation. So I can have a pure rotation kinetic energy for if I know the moment of inertia. And delta U, I've squished it to the, it's due to gravity, it's been squished to the center of mass, and I've got just then mg times the change in height of the center of mass. And by the way, I always like to check, the original work energy, the relationship, W net equals delta K. Well, W net, there's only W gravity, and that's minus delta U gravity, and of course that gives the same equation. Finally, problem 4. We've got angular momentum conserved because there's no torque around the pivot. Gravity, is concentrated at the center of mass. It's been squished to the center of mass. It doesn't give any torque. And the pivot force certainly doesn't. So, initial angular momentum, final angular momentum, set them equal. The initial angular momentum is just the bullet. By the way, let's just quick look at the picture. A bullet comes in. This thing is not moving. It's just vertical in this picture. And it goes through it, it burrows through it, comes out at a lower speed. And we assume that we're looking at a situation where the bullet goes straight through. And then this thing will start to rotate. And our conservation law is going to allow us to figure out what the angular frequency is, the angular velocity is of that rotation. We just need to work out the different angular momenta. Incident, you've got an MVD story. By the way, I'm calling clockwise plus in the formulas I've got here because you see everything, this tends to make a clockwise rotation. This is therefore making it, when rotated clockwise, this would tend to, if I just kind of back up in time, this would tend to make a clockwise rotation too. That's our little recipe, checking with R cross P in a moment. And so let's take CW equals plus, because then I won't have a bunch of minus signs everywhere. I'll just have plus signs. And so back to this. Initial angular momentum of the bullet, an MVD. Final angular momentum, it's an MVD again. The only thing you need to know is that, the V final was given to you. The D, the R, was the same as the initial guy, and the other part is the stick. It's pure rotation around a fixed pivot, so that's I omega. And you know how to do I for a stick through the center. By the way, my final remark is, if I do my L equal R cross P, and I can just prove to you that this guy then does have this MVD form, just like we did in our checkpoint. If I look at R cross P, I have an R here and a P here, and I look at R cross P, it's into the paper, so I define this in my little way of saying a unit vector into the paper, times the magnitude of momentum, times the magnitude of the R here, and R sine alpha. If you just look at this picture, there's an alpha, sine alpha, that's this distance of closest approach. That R sine alpha is D. D is 1/2 L over 2. By the way, I call this R, I really should think of this as D here. And so that's, D was, they said midway between the pivot and the